All right, the first lecture of Unit 4 is going to look at chemical bonds. And usually I have all the bonds in one unit all wrapped together. For this year, just because of the scope of how things are going and you not being able to be with me daily, I've decided to break this bonding unit up into more two manageable chunks. So the first part of the unit is going to be on ionic and metallic bonding. Much more on ionic than metallic. Metallic could talk a little bit about it, but not nearly the amount of as ionic. And then when we're done with this unit, which won't be until probably the week after Christmas break, we'll then probably do a unit on covalent bonding. All right, and then we'll get into chemical reactions. So what are chemical bonds? Chemical bonds is, again, a force of attraction that holds two atoms together, right? And the reason why atoms bond, as we've talked about before, and that's what the last unit is all about, is elements bond so they can become more stable. And usually that means they're going to get their full outer ring is going to be completely full. Sometimes there can be half-filled rings that are also stable as well, but for the most part, elements bond so they can become more stable than what they were before. And that usually means they'll end up getting an octet, or 8 valence electrons in their outer shell. There are three ways that elements can form bond, or three types of bonds that atoms can form for this class. The first is ionic, which is what we're going to focus on this unit, and then next will be metallic, and then is covalent. Ionic is typically found when we have a metal with a nonmetal. Okay? If you remember from last year, we talked about that metals tend to be elements that tend to lose electrons, and nonmetals tend to be elements that gain electrons because metals tend to have a low coulombic attraction, and nonmetals tend to have a high coulombic attraction. And because of that, there is a vast difference in electronegativity values, and metals tend to give electrons to nonmetals. So an ionic bond is one where we see a transfer of electrons. The metal will transfer valence electrons to the nonmetal. And with that transfer, we end up getting a positive ion and a negative ion. And because we have oppositely charged particles, there is attraction. The ionic bond is the attraction between the positive ion and the negative ion due to the transfer of the valence electrons. Okay? And metals tend to lose electrons until they've lost all their valence electrons, leaving full outer shells left behind. Vice versa, nonmetals gain electrons until they get a full octet, their outer level is full, and then they stop gaining, and then they've reached usually their maximum negative charge along with the metal positive charge. Metallic bond is the attraction, it too is an electrical attraction, but is the attraction of the metal cation to free valence electrons. A chunk of metal, if I have a chunk of silver metal, the silver metal is not simply neutral atoms. Actually, the silver has one valence electron, and that silver's one valence electron is donated to what's called the sea of electrons. And so each silver atom donates its valence electron, and that valence electron has the ability to move and migrate throughout the solid. They can move. That's why we treat them like a sea. And the metal cations are like, in essence, like a ship. They're just floating around in the sea of electrons. And because of that, there still is an attraction. It too is an electrical attraction between the positive metal ions and the negative electrons. So just like ionic bonding, metallic bonding is also an electrical attraction between positives and negatives. Covalent bonds is due to the sharing of electrons. And this is usually because we have nonmetals bonded to other nonmetals. So for simplistic purposes, when we have a metal and a nonmetal, they tend to form ionic bonds. There's a transfer of electrons. If it's one metal or multiple metals, they tend to share a metallic bond. And if it's two nonmetals, then they share electrons and they form a covalent bond. When it comes to bond strength, when it comes to the strength of the bonds, ionic, generally speaking, ionic is greater than metallic. So ionic bonds tend to be stronger than metallic. And metallic and ionic tend to be much, much stronger than covalent. So the electrical attraction between opposite charged particles is much stronger than nonmetals where they share electrons. So it's much easier to break a covalent bond than it is an ionic or a metallic bond. Okay? All right. In order to understand ionic bonds, you have to first be able, again, to know dot structures. And in a dot structure, we have the element symbol, and the element symbol signifies the nucleus and all of its inner shell electrons. The dots that surround the element symbol, and whenever we have the symbol of the element, the dots can be placed in any of the four corners. The dots are the number of valence electrons, and we put one dot at each corner. Okay, so if an element has two dots, like you'd see there, we put two dots, three dots, four dots. So if an element has four or less dots, there will be a single dot in any of the four possible locations. It isn't until we get to elements that have five or more valence electrons that we tend to double up and tend to double those locations. Remember, the most amount of valence electrons that we can have is 8, because we'll have two dots at each of the four corners, and that ends up being the dot structure for the noble gases. Okay, so hydrogen is in family 1. If you have an element in family 1, how many valence electrons does it have? 1. So any element in family 1, hydrogen, lithium, sodium, are all in family 1. They all have one valence electron. So it'd be the element symbol, which would signify the nucleus and all of the inner shell electrons it has. And the dot is just signifying how many valence electrons it has. Carbon is in group 14. So it has 4. There's one dot at each of the four corners. Oxygen is in group 16. 1, 2, 3, 4. And then when we come back and double up, and that was really bad, I'm going to come back and redo that one. So it's going to have 2 single dots and 2 double dots. And group 17 has got 3 double dots and 1 single dot. And that single dot could be anywhere. It could be top, left, right. Doesn't make a difference. But you have 2 lone pairs. Oops. Okay. So again, the number of valence electrons is for the representative element. And again, the representative elements are the elements in S and P block. When we have any element in the S and P block, the ones digit of the group number, 17, 7, 16, 6, 14, 4. The ones digit tells us the number of valence electrons it has. Group 1 has got 1. Group 2 has got 2. So the ones digit tells us the number of valence electrons. If you have elements in the D and F block, these elements tend to have either 1 or 2 valence electrons. How do we know? We have to do the electron configuration. And once we do the electron configuration, we should be able to figure out how many valence electrons it has. All right, so once you get the number of dots, it gets to be pretty simple then. All right, so elements in ionic compounds tend to lose or gain or share electrons to acquire a stable electric configuration of a noble gas. We've said that before. The reason why they're trying to get to a noble gas configuration is that tends to be the most stable configuration. And by being in the most stable configuration, that compound tends to exist in that form. All right, so if we look at here, sodium has got 1 valence electron. What would we expect the ion for sodium to become? If you have an element that has 1 valence electron, remember, sodium is a metal. Metals have low coulombic attraction. So do we expect metals to lose electrons or gain electrons in an ionic bond? Because they have low coulombic attractions, they would tend to expect that they lose. And they lose the number of valence electrons it has. So sodium, when it forms an ion, will lose that valence electron, meaning there will have no valence electrons left. And the atom of sodium that has 1 valence electron has now become the sodium plus 1 ion. So metals tend to lose the number of valence electrons they have to become a metal. Okay? Sulfur is a nonmetal. Sulfur has 6 valence electrons because it's in group 16. Nonmetals tend to have high Coulombic attractions, and so they do not lose electrons very easily. Vice versa, nonmetals tend to gain electrons. So how many electrons would sulfur need to gain to become an ion? 2 more. So when sulfur gains 2 more valence electrons when it bonds, it now has gained 2 more than its atom state. So therefore, in its ion state, it would develop a charge of -2. So sulfur gaining 2 more electrons, reaching 8 valence electrons around the outer ring, now has a -2 charge. We would then call it its ion form. Okay? So this would be the sulfur ion. Real quickly, why don't you pause the lecture now and go ahead and complete calcium, oxygen, and zinc and see what type of charge you'd expect to see on each of these elements. All right, calcium's got 2 valence electrons, so we would expect it to lose both of them and to form a +2 cation. Oxygen has got 6 valence electrons, just like sulfur. They're in the same family, right? Periodicity. So it too would need to gain 2 more to become full and become a -2 ion. Zinc, I gave you the electron configuration because zinc is in the D block. So if I look at here, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. How many valence electrons does zinc have? Hopefully you identified 2 because 4s, the number 4, is the highest coefficient. So zinc has got 2 electrons in the 4th floor. All of the other electrons are on the 1st, 2nd, and 3rd floors. So those are the valence electrons. So zinc has got 2 valence electrons. So we would anticipate that as an ion, it would lose those 2 valence electrons, being a +2 ion. And if I look at the electron configuration then, the electrons that are lost are the 4s electrons. So the electron configuration of the zinc ion would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, because the 4s electrons were lost when it forms the ionic bond. The 1st floor, the 2nd floor, and the 3rd floor are completely filled and the most stable configuration of the zinc ion. All right, let's turn the page. All right, so again, a positive ion is called the cation. So metals tend to lose electrons to form cations. Nonmetals gain electrons because they have high Coulombic attractions, and those are anions. So it's the attraction of the cation to the anion, and that electrical attraction is the ionic bond. All right, so your homework is going to be to finish this table, but I want to do problems, a couple problems with you, and then the rest of them I'd like you to do on your own, and then check with the answer key, which will be your homework for Wednesday. Okay? All right, magnesium and fluorine. Again, whenever we have an ionic bond, we are going to have a metal and a nonmetal. The metal is magnesium, the nonmetal is fluorine. So magnesium has got 2 valence electrons because it's in group 2, and fluorine has got 7 valence electrons. It is a halogen. So to become full, how many valence electrons does fluorine need to gain? Hopefully you said 1. So one of the magnesium electrons will transfer over to fluorine, making fluorine full. Fluorine does not want to gain the other electron of magnesium because then it would go over the octet and become less stable. It doesn't do that. So how do I make sure that magnesium becomes stable? Well, when these compounds react, there are millions and millions of these particles around. So another fluorine atom has to come around and take the last electron of magnesium. Okay? Now magnesium has lost both of its electrons and has become the most stable because now what's left behind is full outer shells. Okay, so therefore, in the workspace, that's what you need to do. You need to keep adding metals and nonmetals until the number of valence electrons is met and everybody is full and happy. Okay, so the Lewis structure now of magnesium with fluorine would be the magnesium would no longer be an atom, but it would become a +2 ion because it has lost 2 valence electrons. Each fluorine has now gained 1 electron, becoming -1. Now, when I draw the Lewis structure, I would not put another F next to an F. I would not do that because then there would be 2 negative particles next to each other. So you need to be very cognizant of making sure that positive and negative particles are next to each other and not positive with positive and negative with negative. So the Lewis structure with magnesium and fluorine would be 2F atoms, which will become now 2F ions, -1, and magnesium is +2. When you are done, if you've done a correct Lewis structure, there should be no charge left. -1 +2, -1 adds to 0. There is no charge. So each of the particles is charged, but the overall structure is uncharged because they summate to 0. The formula of ionic compounds always begins with the metal, and the formula for this compound would be MgF2. 1 magnesium and 2 fluorines would come together to make, we call this a formula unit. A formula unit to an ionic compound is just like the word molecule to a covalent compound. A formula unit is the simplest whole number ratio of metals and nonmetals that summate to a 0 charge. 1 +2 and 2 -1s add to 0. This is called the formula unit of the compound magnesium fluoride. All right, pause the lecture here now and go ahead and do letter C. Jump down and do letter C. I'll show you the answer here in a second once you unpause me, and try to do it and see if you get the right formula and Lewis structure for it. All right, coming back, aluminum. Aluminum has got 3 valence electrons. Each oxygen has got, each oxygen has got 6. So aluminum is going to transfer 2 electrons to oxygen to fill that oxygen. But there's 1 electron left on aluminum, so we need another gainer. So another oxygen comes by and takes that electron of aluminum. Now aluminum has no more valence electrons left. It is done gaining. Are we done? No. Now there's that oxygen has got 7 electrons but needs 1 more. So now another aluminum comes by and takes 1 of the aluminums. Now that oxygen is full, but now that aluminum's not done. So we now need another gainer. But now you can see that this aluminum has 2 to give and that oxygen has 2 to take. So now the correct ratio is 2 aluminums to 3 oxygens. That would be the correct ratio in order to get to the formula unit. Each oxygen now has gained 2 valence electrons, becoming -2. And each aluminum is +3. -2 +3, -2 +3, -2 adds to 0. So the correct ratio would be 2 aluminums for every 3 oxygens. So the formula of aluminum oxide would be Al2O3. So keep adding metals and nonmetals until the correct ratio results in 0 charge left over, where all the cations add to 0, the simplest whole number ratio, and see if you can draw. So what you've drawn now is the Lewis structure is in this column and the formula is in this column. So this is how we draw Lewis structure for ionic compounds. It's the lowest whole number ratio of ions that results in a 0 charge. And that's how we make ionic compounds and their Lewis structures for them. All right, so finish the rest of these. I think there's about 1, 2, 3, 4, 5, 6, 7. There's 7 of them left. Complete these. I do have the answer key online now, and you can see how well you did off of these problems. All right? Thanks for listening.